You unlock this door with the key of imagination. Beyond it is another dimension. A dimension of sound. A dimension of sight. A dimension of mind. You're moving into a land of both shadow and substance, of things and ideas. You've just crossed over into the Twilight Zone.
Hello. Let's go on an adventure together. Organic for dummies. Shh, we gotta be quiet. Let's go learn about formal charges and resonance structures.
Rule number 1. Resonance structures occur in species where there are more than 2 or more valid Lewis structures. Structures are valid if every element contains a complete octet. Rule 2. The resonance structures are basically imaginary. They don't exist. The averages of the imaginary resonance structures make up the hybrid structure, which naturally occurs, the real ones. The structure hybrid has the least formal charge, we'll talk about it later, and is the most stable structure.
If 2 resonance structures have the same formal charge, they will contribute equally.
If one structure has an overall lower charge, it contributes more, causing an unequal contribution to the hybrid. Resonance structures provide a delocalization of electrons, basically meaning the different resonance structures give more options of where the electrons can be. So, more places equals more delocalization, which means more stability. The more equivalent the resonance structures are, the more it contributes to the stabilized structure.
As she previously explained, these 2 benzene rings contribute to the final hybrid equally. So the 6 electrons that are delocalized are equal in the benzene ring.
All else being equal, the greater number of resonance structures, the greater the stability. Woo! Valence electrons for each element determine how many electrons will be in the structure.
And now we're going to do an example of how to get formal charge from resonance structures. First, we have to get the Lewis dot structure of the compound that we're doing. And we're going to do NO3. First, you have to figure out what group it's in. And nitrogen is going to be in group 5, and oxygen is going to be in group 6. So the total amount of valence electrons that we're going to have in like oxygen is going to be 18 total. That's going to go into the structure. The total in nitrogen is going to be 5, and that's going to go into the structure as well. And then since it is a negative, it's going to be another electron, which is going to be added into the total structure, the total resonance structure. So that's going to be 24. All right, now we're going to view an example visually of resonance structures with formal charges. And NO3 minus actually has 3 different resonance structures. The first one is this was the second, and this one is the third. As you can see, the nitrogen is in the middle, and the oxygens are surrounding it. The oxygen's electrons, where the arrows are pointing, that's where the electrons are delocalizing. As you can see, the formal charges for each and every element is labeled and is going to be 0, but the oxygens are going to have different formal charges attached to them. And we would derive the formal charges from the equation, which we'll learn about later on. The also overall charge of the whole structure is going to be negative. As you see, it is NO3 minus. Thank you.
This is a resonance hybrid structure of NO3. It is also the most stable. From the 3 we drew earlier, if you were to add them up and then average them, this is what you would get. Its bond energy is spread out equally among the 3 oxygens.
Okay, so here is the electronegativity chart. It increases from the bottom to the top, and then also from the left to the right, going over to helium, with fluorine, oxygen, and nitrogen being the most electronegative of the elements. All right, so here I'm going to briefly go over bond dipoles, and these happen in covalent bonds where the electrons are more likely to be around the most electronegative atom. So in this one, it would be carbon, because it's slightly more electronegative than the hydrogen here. And the most electronegative gets the partial negative charge, where the least electronegative gets the partial positive. And the dipole arrows go from the least electronegative to the most electronegative. And in this one, it's not a very polar atom. And then over here with the fluorine and the hydrogen, it's very electronegative. And the bond dipole will be much bigger in this atom than it is in this one.
We're going to summarize what we went over today. Let's get on this level. Resonance theory is what we went over. You have to have two valid Lewis structures. And the resonance structures, all of the resonance structures are going to make up one single hybrid structure. The hybrid structure is going to be the most stable structure that we have. So the more structures, the more delocalization, which is the movement of electrons through the structure, the more stability that we have.
The second thing we learned is formal charge. The equation to find a formal charge is you take the valence electrons minus the number of bonds plus the number of lone pairs. The definition for a formal charge is, in a given covalent bond, half the electrons are assigned to each atom involved in the bond. The third thing we learned is electronegativity. The definition of electronegativity is the ability to attract electrons in a covalent bond. Electronegativity increases bottom to top, left to right on the periodic table. The fourth thing we learned is dipole-dipole, which is the separation of partial negative and partial positive charges. The delta plus means that you are less electronegative. The delta minus means you're more electronegative. When you're drawing the double arrow, you always draw it from the less electronegative to the most electronegative.
Rises from francium to
Hello! Let's go on an adventure.
Where are we going? What are you doing? You had one line to say.
Hello!
Is all you could say is hello? Is that it? Is that all you're gonna tell us?
I need a drink first.